Hi, I have my very high performance ADC board here. So first I'm going to show you the features of this board, then a little bit of the schematic design, and then go through comprehensive measurement results to see really what it is made of. This is stereo ADC. So we have two balanced differential inputs here on the pin header. Then we have PCM output, I2S output. Everything is configurable with these jumper links here, so there's no programming is needed, although it can be used also in I2C mode with Arduino or something similar. The PCB is a 4-layer design. It's rather complicated board, although there is some space here, because first I had the reference designators on the silk screen, but I removed them. There's also some exposed copper on the bottom side to make it easier to solder some of the components, because they have thermal pads, some of the SO8 packages and the ADC as well. There is a reset button, because the manufacturer recommends to reset the device every time you change any of the settings. Supplies are connected just here on the pin header, so there was no space for screw terminals. This can also be used in mono mode by combining stereo channels. You get 3 dB improvement in dynamic range. Of course, it increases the cost for a stereo application if you need two mono boards, which cost almost the same as a stereo board. All the components here are very high quality, so we have some quite expensive op-amps, good op-amps here. The ADC chip, of course, AKM, one of their top ADCs. In order to get the high performance, of course, you need to have low noise, low distortion input circuit, and references must be solid, clean. In terms of the jumper link settings here, so first we have a high pass filter. There is some DC offset in the input circuit and in the ADC itself as well, so it's actually good to have the digital high pass filter always on. Then there's two links for the digital low pass filter selection. So there's sharp, slow, short delay, sharp, short delay, slow, a selection between 24 and 32 bit data out. Then we have a master slave selection. Then we have these 4 bits are for clocking selection. If you have it as slave, then it's just basically automatic, because it just takes whatever clocks coming in. But if it's master, then you use these jumper links to select the clocks. These larger capacitors here are the input coupling caps. So we have this dual jumper links in between that you can sort the caps to get it DC coupled input. Then we have one LED for power on and another one for overflow, which blinks if the input clips. There is a possibility to bring master clock to a proper S&B connector instead of the pin header. On the bottom side there are some instructions how to configure the stereo mono mode by soldering one resistor, or control mode to get the I2C. Also, most of the setup inputs here on the ADC, so they use 0 ohm resistor, so if you need to change something, it's kind of possible by removing a resistor and soldering some wires there. I'm briefly going through the schematic design of this ADC. This is of course only part of the whole design, and to get the high performance there's also a really careful design 4-layer PCB layout, but I'm not gonna go through that. Here's the overall design, the root sheet and the KiCad I'm using to design stuff. Here's the ADC chip. Here we have power supply sheet, and then the inputs, 2 input paths coming in. There's a bias, the setting jumper links, and so on. So let's first have a look at the ADC. Signals coming in here. Then we have the PCM output just going to pin header. Master clock is coming from outside. It can be given in the pin header or taken through a proper SMB connector. Here we have some decoupling caps for the power supplies and references. Here is a reset button because it's recommended that if you change any settings you should reset the device. And then we have an overflow LED, so if the input signal is clipping, this LED will flash. By default, the ADC is used in hardware or parallel mode, so you configure everything with jumper links in the pin header here. Other than this, it can be used in I2C mode. It's also possible to wire the I2C here using some of these pins here, but by default you don't need to do any kind of programming, just put a jumper links on the settings you want to use. Okay, let's have a look at these other sheets. So power supply, it's very simple, just a regulator for 3.3 and 5 volts. Plus minus 15 are coming in and used directly. So these, for example, this LDO, it's a good one. It's relatively low noise, but it's nothing like extremely expensive. But it works really well in this application, get a super performance. Well, this is kind of part of the power supply as well, of course. So the most important one is the reference one. So here we have a large 1000 microfarad cap with a series resistor, and this reference input seem to be fine with this. With some AK DACs I've used, this kind of thing doesn't work. It needs very low impedance. Then the most important bit are input paths. Let's first have a look at the bias. So there is just a simple bias. So we have a resistor divider to get the half of the supply, and it's buffered for both input channels separately. So this is used as a bias for the differential amplifiers. The input paths we have normally used as the pin header coming in. There is a possibility to use XLR connector as well. So first of all, this board was initially designed for measurement applications, audio measurements, not to use as a Hifi ADC. It can be used and it's going to be excellent ADC. So you could use just the XLR and use it directly. But the idea was that if it's used for measurement applications, there will likely be some kind of scaling circuit in front of the ADC, so these signals would not come directly from the device under test. Anyway, signal coming in, we have just a very simple filtering here. These are a little bit larger plastic caps which can be sorted with this jumper link, so if you want to have AC or DC coupled input. Then we have some simple protection which is good enough to protect the ADC chip from some basic stuff, but if you really use it for a measurement device, it should be more robust input protection. First of all, the resistors here are only 100 ohms to get the low noise, so if there's any kind of overcurrent condition going, these resistors and the small diodes cannot really take a high current, so you would need to use something here in front to actually limit the current or switch something off. Anyway, these diodes work as a simple clamp, so we have here like a clamping circuit. So overall the voltage after this, which goes to ADC, it should be at least not much more than the minimum voltage, but it's not easy to to limit it at a certain value with a simple circuit. Anyway, after this simple protection, we have just the buffers separated for both channels, and then we have the differential amplifier, which get the bias, so these outputs of the differential amp will have a common mode voltage of 2.5 volts and going to ADC. And the whole thing here is a low pass filter to filter out high frequency components that they won't alias in the ADC. The maximum sample rate of the ADC is 768 kHz, and corner frequency of this input low pass filter is high enough that even if you want to use this highest sample rate, you can do it with this filter without any modifications. So this, of course, is the oversampling ADC, like almost all of them are these days. Sample rate is 6 MHz or so, the filter frequency is not very critical and it can be quite high. If you're going to use this ADC as monoport, then everything kind of from here to left is not needed in one of the channels, because this point here, the buff out, that's actually going then to the other channel. So this part would be in both channels. The whole point of the mono thing is that you have two of these separate circuits, you have two channels, signal will be summed, so signal will be amplified by 6 dB, but noise, since it's different input circuit, it's uncorrelated noise and it's only going to be amplified 3 dB, so you gain extra 3 dB SNR by doing that, but cost is almost doubled, so it's up to you to decide if it's worth it. For measurement applications, it may be nice to have two mono devices, because then they are identical, and even the small channel differences you have between left and right channel may be gone when using a mono device. Okay, let's have a look at the measurement results. These have been measured with Audio Precision AK5572 audio analyzer, which is pretty much the best audio analyzer money can buy. This is the signal path setup, so it's analog balanced going into the ADC, 24-bit I2C signal coming out at 192 kHz sample rate. The maximum level is 3.6 volts input differential. So here are the key THD+N performance numbers. We see a little bit of difference between left and right channel, which is quite common. So the spec for this chip is -112, so -114 is already 2 dB better than the spec is. Here we can see THD+N, so that includes the noise, THD, that is without noise. So if you use this, for example, for measurement application, that may be important for you, the THD only. And these are with the -1 dB signal level, so -1 from 3.6, which is the maximum 0 dB level. And all these measurements, they use 20 kHz low pass filter, so measurement bandwidth is 20 kHz. Here's the noise level, -119 dB, A-weighted 121. So here we see A-weighted SNR and dynamic range 121 dB, which is spot on with the spec. Here's a frequency response. These small deviations, I think at least this one, the low pass one, is from the measurement setup, from the AP. This, I think it's the digital filter of the ADC. So yeah, if you look at the scale, it's ±1 dB, so these are very, very small deviations. So here you actually see the deviation, which is a bit smaller than here, I believe, because it actually removes some of the effects of the measurement setup. So anyway, 0 dB in practice. No phase difference between channels, just a kind of sanity check. crosstalk is very high, 130 dB. So this is a stereo ADC. You can use them as a mono device, when the crosstalk essentially should be even better, although this kind of number is basically no crosstalk at all. So one benefit of using the mono device is that you at least you don't have the channel difference between left and right channel. Here is the THD+N ratio. The figures we saw in the first page, so they were basically here, -1 dB. And here we also see the small difference between left and right channel, channel 1 and 2 here. So otherwise it's equal between the channels, but just very close to maximum level. There is this a small 1 dB difference or so. And this sharp spike rising here is just because it starts clipping. Here's the same for a THD. Again, could be useful to know for measurement applications. So it's a little bit better than THD+N, because here we have the noise part as well. So this is a level, same measurement, but showing absolute level instead of ratio. So basically this is our noise floor with small signal levels. So that's the -119 dB we saw in the noise figures. And again, the same for THD only, without noise. This is THD+N ratio versus frequency. So the previous one was versus level. And this is at -1 dB level. So basically this graph, this spot, the point here, 1 kilohertz, is the same we saw here. 1 kilohertz, -1 dB. So that's why we see the difference between the channels in this graph, because it is basically at the maximum level. If it was a little bit lower level, they would be equal. So basically what you want to check in this kind of, it's more or less flat. It starts going down a little bit at the higher frequencies because we have 20 kilohertz measurement bandwidth. So at this point we start losing the harmonics. Basically above 10 kilohertz we don't have any harmonics anymore. For example, when I was developing this ADC, I had some increase towards higher frequencies, and it was due to the protection diodes in the input path had too high capacitance. And that was also type of measurements that I couldn't see it in the just a single spot THD+N measurements. Again, it's the same for THD without noise. This is FFT spectrum without signal. So basically it shows the noise shaping. So we have a clean, very low noise floor and in the 20 kilohertz audio band, but then it starts increasing. And that's again has no meaning in actual audio applications, but if you use for measuring audio devices, then you may be interested that this may not be good for you. That if you want to do high bandwidth measurements, there's 1 kilohertz FFT. So we see the harmonics here. Overall level is very low, so almost -120 dB. The same for 10 kilohertz. And that's it for the measurements. And just a little bit of marketing words at the end after the measurements. So what those figures we've measured, what do they actually mean? How do they compare? Here is a Prism Sound Atlas, which is apparently a very high performance audio interface. Cost 4,000 euros at Thomann. So if you look at the analog input specs, THD -117, THD+N -111. So THD is a little bit better than measured now in this my ADC board. 116, 114. But THD again, it's better, 114, quite significantly better. Dynamic range 116 here. We have 119, this unweighted. So pretty comparable, like some results are significantly better, some a little bit worse. Of course, having a product like this is a lot more than just the input performance or output performance. There's a lot of things inside, but just from pure technical figures perspective, it's very, very good. Also, seeing spec numbers like that, you don't always know what are actually the conditions and what does it mean. Is it average, is it min or max or typical? But I think quite often you can assume that it's the case what gives the best figures for the marketing department. Here, for example, there are some conditions like they are unweighted, so they're not A-weighted, like it's often to get nicer numbers. But for example, in my board now, there's a difference between left and right channel. If I would put them on a paper, would I put the average or the best or the worst figure? Yeah, you never know. And they always represent something like typical, especially when you're doing some very high performance stuff. You will never get that every single unit would be as good. So you just need to state it as a typical performance, and then if something falls a bit behind, you can still say that it's not guaranteed the minimum performance, it's typical. It's the same for the chips as well. Like this ADC chip, for example, yeah, it's 112 dB THD+N, but that's typical. The minimum is actually 100 dB. So there's a huge 12 dB difference between their minimum and typical specification. So you could get a chip from the production line and it's 10 dB worse, and you still couldn't actually complain that it's out of spec. That's how they secure their own position by claiming just the minimum spec to be something completely different. So yeah, there's always a lot behind the numbers you see.